So in the previous example, we were showing whether or not a particle was in static equilibrium. This time, we're being told that it's in static equilibrium, and we're going to use that fact to figure out these two unknown forces. So we don't know F2, we don't know F3, so we're going to figure those out. So let's do it graphically first. So just write that out. Now, I think I already drew this to scale, but let me just quickly double check. No, I probably haven't drawn it to scale because we don't really know what things are yet. Let me just see if I drew that one. Yeah, I did. So what I might do, I'll just start again. So we know we've got 20 downwards. And for graphical, if we've got particle equilibrium, then we should get a closed path, so we can use that to figure out the missing forces. So I'm just showing my scale here, just so people know it's a scale drawing. So that's going to be 10 newtons, 10 newtons. So we've been given this force, the 20 newtons. We don't know F2 or F3, but if we're going to put them nose to tail, so let's take the F3 down first. We don't know how long it is, but we do know what direction it goes in, so it's line of action. So what we're going to do is we're going to take that angle, so that 50 degrees, and we're just drawing where its line of action. So if it was going to nose to tail, it must start from that vector, and its line of action must come up here like this. Let me just change the color of that. Now, so that's the line of action of F3, and then we've got F2, which is at 35 degrees, so we know its line of action, and we know that if we've got static equilibrium, it must come back to this point. It must make a closed path. The resultant must be 0. So if that went somewhere else, so say we had that vector and it came here somewhere, then that wouldn't be in static equilibrium because you'd have a resultant force. There'd be a force from the end of this to where you start, or from where you started to the end of this would be a resultant force. So you wouldn't have static equilibrium. So we know that this line of action, it must come back to the start of that original vector. And so we know its line of action must be here. And we know that it ends here. So the nose of this vector F2 must be there. And the tail of F3 must be here, and they must join together nose to tail, so the other end of F3 must be there. I've probably drawn this a bit small to get an accurate answer, but anyway, we're just doing this to get an approximate answer. 50. So we now know that F3 must be like that, because they have to all join together nose to tail and take you back to where you started, because it's in static equilibrium. That's F2. Let me just shuffle that across, save a bit of space. So therefore, F2 equals, so let's measure that. So 10 division was 10 newtons. So that's 10, 11, 12, about 13. So it is approximate because it's just a scale drawing and it's a bit small really. So this is not going to be too accurate, but it's about 13 and we're newtons. F3 must be approximately equal to 10, 15, 16, 17 must be approximately equal to 17 newtons. Okay, so that's okay. Now the second we can do it is using trig, so we're going to use the same thing as when we're combining vectors. And so we're going to have a look where the x and y components are. We're going to check all the x components add up to 0, all the y components add up to 0. So let's have a think about this for a minute. What we might do is just use this sketch directly. Put it over this side. And this is going to be a numerical solution. So we're going to use trig, and we're going to use the simultaneous equations that we did a bit of revision on in a previous video. So first I'm going to have a look for all my x and y components. What colour I'll use here? I'll use blue. So that is just going to be, we'll call this F1, and it's just going to be F1y because it's only got a component in the y direction. Just looking at that, and it's negative. We should just put on, this here's nearly 90 degrees. If it had been 90 degrees, I would have done my x and y axes aligned with those, but it's not quite 90 degrees. So this is 50, 35, they all add up to 180. So that must be 85, this angle in here. Oh no, 95, sorry. 50, that's 85, yeah. So this must be 95, this angle in here. So not quite got a right angle, so there's not going to be any benefit in doing the x and y axis aligned with those. So what we'll do is just normal x and y, I think. So we'll do the y-axis vertical, x-axis horizontal. Okay, so we've got F1y, we're going to call this one here, we'll call that F2, just do that in, oh well, it's already F3, sorry. So let's get rid of that. So this is going to be F3. And we're just going to have a look for the components of those. So component of this one, like so. Like so. So this is just exactly the same as what we did when we were combining or adding vectors. So this is going to be F3x, it's horizontal. This one is F3y. This way. We've got F2x and F2y. So let's start with the x's. So we know that F1x is 0 because it doesn't have an x component. This is F1, the 20 newtons that we were given. It's only going vertical, so no x component, so F1x is 0. F2x equals, so we're still thinking about SOHCAHTOA, but I'm not going to write those down anymore. We're just going to figure it out. So it's going to be, this is adjacent to this angle. Your hypotenuse is up here. And so we're going to write that in terms of F2. So it's going to be F2 adjacent. So it's cos 35. Don't know why I'm doing all this stuff in blue. Let's just figure out what cos 35 is. Zero 0.8192. So that's going to be F2 times 0.8192 is what this is. But usually write the number first. So 0.8192 times F2. All good. And then we're going to find the x component of F3, so F3x. So there's our F3, there's F3x, it's adjacent, so it must be hypotenuse times cos 50 degrees again. So F3 cos 50. So you just have to be careful with that. Don't assume that just because it's the x, it's going to be cos. It's not always. Sometimes you're given this angle up here and the x component can be the y, the sine, sorry. The x component can be the sine of the angle if it's the one up here. In this case, it's more common that you get it to be cos, and that's what it is in this case. F3 cos 50. Let's figure out what cos 50 is. 0.6428. Let's put the number first. Okay, so what we've done is we're looking for the x and y components. This time we don't know these values, so we just keep those as letters, but we can figure out the cos of the angles. And so we've got all of the x components, and then we're going to use the fact that they've got static equilibrium. Therefore, you must have the sum of the x components of the forces must be equal to 0. So that means that F1x, we'll just write out in full, plus F2x plus F3x. So when you're doing the tutorials or the exam, you just need to judge how much working you have to show to make it clear to someone what you're doing, and which won't always be quite as much working as I do, just to make it clear to anyone who's reading this what you need to do. 3x must be equal to 0. F1 is just 0. So therefore 0.8192 F2 plus, okay, so I'm just substituting this in, F2x is equal to this, so I'm just putting that in there, plus 0.6428 F3 is also equal to 0. So I've used the fact that all the x components add to 0, and then I'm just substituting in those x components in terms of the original force. And this is just to limit the number of variables you end up getting. So what you'll see is we'll then go into the y, and it'll also use F2 and F3. So we'll end up with two equations, two variables, like we talked about in simultaneous equations. That's going to mean we can find those variables. If we just left it as F2x and F3x, we'd have F2x, F3x in this equation. Then we're going to have something to do with F2y and F3y in the next equation. We'd have 4 variables in 2 equations, and we wouldn't be able to solve it. So that's why we're doing this. You're writing it in terms of F2 and F3 so that we end up with 2 equations, 2 variables, and we'll be able to find the answer. We're going to call this 1. And we notice it's got a 0 here, so we're going to be able to use that shortcut we talked about, or this is the equation we're going to use first. We're going to write F2 in terms of F3 using this equation because it's got that 0 here. We've got no constant on the other side. Okay, let's go the same thing. What I'll do is I'll do the same thing with the y components. We'll just fast forward through that, and then I'll meet you on the other side. So we've gone through that. We've figured out what all of the y components are in terms of the original forces, F2 and F3, just using the trigonometry again. And we've used the fact that the sum of the y components must be 0 because you've got static equilibrium. Therefore, we can just add up all the y components. We substitute in these values in terms of F2 and F3. So now we've got a second equation that involves F2 and F3. So we've got 2 equations, F2 and F3, and therefore we can find out what these values are using simultaneous equations. The other thing I did was I just noticed that firstly this 20 was negative, so I made sure that's negative. But the other thing was that F2x was also negative, and so I corrected that. So this is negative, that value, so it's negative down here. So now we're going to take, because this one's 0, we're going to use that one, and we're going to write one of these variables in terms of the other. We'll probably just do F2, and so we'll figure out what F2 is in terms of F3, and then I'm going to substitute that into this equation. So let's just figure out what F2 is in terms of F3 first, using that equation 1. So we're getting there. I have to move this stuff down here a bit further. I might go back up anyway. So now we've got F2 in terms of F3, then we're going to take this and we're going to substitute it into the other equation. And so this came from equation 1, this one up here. So we're going to substitute this into equation 2, and then we'll get one equation. The only variable will be f3, and so we can solve it. So let's do that now. So we've now figured out what f3 is. Equal to 16.45, just checked back to the scale drawing. We've got 17 previously. It's near enough given how small the scale drawing was. So that looks pretty good. So now we've got f3. Then we're going to substitute this back into, what do I want to substitute it into? The easy one, where was that? Yeah, f2 is equal to 0.7847 times f3, so we'll substitute it back in here, and that way we can get f2. So now we've also got f2. I'm just underlining it because I've checked it against the scale drawing. If we had a little, well, we have got time, I can fast forward it. What we'll do is I'll just double check that those work in these two in the original formulae. So in formula 1 and formula 2 here. So I'll just check that they work in there and we get the right answer. We get 0 for formula 1, we get 20 for formula 2 on the right hand side. But if you were in an exam, you'd probably be, well, if you'd done a slightly better scale drawing where it's a little bit bigger, you'd probably be confident enough because you checked it against the graphical solution. But let me just check it numerically as well, just to show how you do that. And then we'll make sure we've got the right answer, and then that'll be us done. So the checks worked out fine for both equations, and so we can be confident to write down the answer and underline it. So just a quick summary again of what we did here. So graphically it's quite easy, shows you how powerful the graphical solutions are, and if you do it big you can get quite accurate answers. Also, if you do it in a drawing package like AutoCAD, you can get very accurate answers, just as accurate as the calculations. And so it's always worth thinking about just doing a quick graphical solution, especially to check your answers. But we did the graphical solution. We figured out that F2 was about 13, F3 was about 17 newtons. Then we looked at the numerical solution. Just going to tidy that up. Numerical solution. So to do that one, it's like when you're combining vectors, you find the x and y components. And then what we want to do is get two equations with two variables. So what we do is we write the x components in terms of the original forces, F2 and F3, and we also write the y components in terms of F2 and F3. Then we use the fact that for a static equilibrium, the sum of the x and y components must be 0. So that then gives us two equations. Because we've written the x and y components in terms of F2 and F3, then we get two equations with two variables. Because we've got two equations with two variables, we can then solve it using simultaneous equations. In this case, we noticed that one of those equations had a 0 value, so we used that first, and we used that to write F2 in terms of F3, so just using normal algebra to rearrange it, F2 in terms of F3. Then we substituted this into the other equation, equation 2. What did that mean? It means that you end up with one equation which has one variable in it. So you're basically eliminating this f2 by writing it in terms of f3. You've eliminated that variable, so then you can solve that because you've got an equation with a single variable in it. You can find f3. Then you use this again. You substitute the value you've just figured out back into here to figure out f2. You've now got your two answers. In normal situation in an exam or in a tutorial, it'd be enough that you check that against your scale diagram, but in this case I've also checked it back into the equations, and so that would be an alternative. If you didn't want to do a scale diagram, you could just check it by putting it back in the equations, make sure you get the right answers. So for equation 1, I confirmed that I got 0 when I worked this out for the values of f2 and 3 that we'd figured out, and I also found that I got 20 when I substituted f2 and f3 into the left hand side of this equation. Took a while, but that's it. Okay, let's move on to looking at some more practical problems, or some more realistic problems, not just particles, but what do we do in real problems involving physical objects.